Okay, good afternoon, physicists. We're going to take a look here today, this idea of pair production, and then another idea on matter waste. So neither topic, is going to require a lot of time for us to at least be familiar with the effect and, have some sort of, reasonable expectations of understanding, at least, parts of what's taking place here. But in 1905 or so, Einstein really laid down the framework for pair production. But it's not really until probably a couple decades later that I think people are able to kind of start putting this maybe into practice and seeing how to put this into practice. And then the nuclear physicists really got a hold of this idea and ran with it in the early 1980s. And I think Carlo Rubbia of CERN will win a Nobel Prize for, really constructing an experiment on a grand scale, being the director of CERN labs, and using this idea of really, kind of pair production, but kind of in reverse. So let's kind of take a look at, what's really going on here, and then we'll look at some of the details, and maybe a calculation or two. But pair production really is the idea of energy and mass being somehow equivalent in the name, in the eyes of nature. And so you get this idea here, E equals mc squared. And, the idea of sort of, pure energy is really a photon. And, that's really, like a particle of light. And this m right here, this is, rest mass, really. So that somehow like a photon and something that has rest mass, could be an electron, could be a positron, proton, neutrons, muons, any of the hadrons or leptons, it makes no difference at all. As long as it's got rest mass, somehow it's equivalent to somehow like a photon or something like that. Now, in this idea of pair production, we have to really follow the laws of physics that we have discovered so far. And so, those important ideas, are not foreign to you really here at all, okay? And so something like our great conservation laws are really going to be the cornerstone of really what's taking place here. And we don't have to look too much further than that to really get a good idea of really what's taking place here. In all interactions that we have seen, and at this time, we're talking billions of closely monitored interactions between particles, and this is happening in nuclear reactors. This is happening in particle accelerators. There are universities that would have maybe a multitude of particle accelerators. Last time I was at the University of Reno, they were building several of them. And, and you just build them from scratch, right? There's no catalog where you sort of pick up and say, yeah, I want that particle accelerator. And, they were probably, about the size of a, maybe like a lab table, at MJC. So, my laboratory could, hold like 6 of these particle accelerators. So, they don't have to be big. And, they were interested on kind of medium energy collisions and so forth to really kind of understand the idea of fusion, what's taking place in the sun. So when Lawrence develops the cyclotron around 1930 or so, maybe a year or two before that, there's a race to make the cyclotrons bigger and bigger and bigger because you can get the particles going faster and faster and faster. But it may be that there's a lot of very interesting physics that takes place at very moderate energies, and we see that all over the universe, in stars. But this is our guiding light right here. The charge is conserved in billions of these interactions that have been watched. Right? We've never seen charge really disappear from the universe. Okay. energy is conserved. And, maybe we have to be careful on what we mean by energy, because it's really kind of this energy mass now. Because mass is just another form of energy. It's kind of like a potential energy. If you've got mass, you've got the ability to have this energy, and we call that rest energy. And momentum is conserved. And so when we take a look at a photon, okay, that is a particle of light, it has no charge. So light, when you turn on a light bulb or the light from the sun hits you, right, you're not feeling, any charged particles or anything like that. There's really kind of like no mass there. There's no electric charge there either. But there is energy. That is, there's the ability to do work. So the rays from the sunshine, from the sun, can move material around, right? So if you're small and you get hit by, electromagnetic waves, yeah, you can be pushed around, especially if you're a charged particle, because there is this oscillating magnetic and electric field in there that, can affect charged particles and so forth. And the photon carries momentum. So it has no rest mass, but it carries momentum. It has no rest mass, but it does carry energy, but it carries really no charge. And the idea of pair production is that we can get something like a photon, and it can turn into something that has mass. Or you can actually do what Carlo Rubbia did, get mass and then turn it into a photon. And so the physicists have been able to kind of work this really both ways. But a photon, as it kind of goes through space, is carrying no charge, it's carrying energy, and it's carrying momentum. And so if it has some sort of interaction, and in this case, I'm going to call this interaction a pair production interaction, it has to have that interaction such that the charge is conserved, energy is conserved, and momentum is conserved. And so, we're going to be very, very careful now with this idea of, what is being conserved. And once again, this idea of mass is just another aspect of energy, and we have to really watch that. But in pair production, what you can have, for example, so you can have this photon, okay? And right, this thing has no charge, okay? But it does have energy, right? But it has energy, and it does have momentum. Now, what it can do is it can break into massive particles. That is, the photon just becomes mass. But it has to do so that charge is conserved. And so something that is pretty common, like at the Stanford Linear Accelerator, is that you can create an electron. Okay. Now the electron, though, has negative charge, right? So there is one negative charge sitting here. And you have some sort of rest mass, right? So you have the rest mass. And in this case, it's an electron, so that's about a half of an MeV. Now, the photon cannot turn into an electron. This would violate conservation of charge. I started with no charge, but now I have charge. Right now, I've got some negative charge. And so what we see happen in our accelerators is that we make a pair. We make an electron with a positive charge. This is called a positron. And they were, theorized to exist in the late 1920s or so. I think Paul Dirac's work won him a Nobel Prize for this. And, then they're found shortly after once you start looking for them. And this has, one positive charge. And it has a rest mass of the electron, right? It is exactly an electron, just with the opposite charge. And so if the photon has enough energy, it can create a pair of massive particles. That's where we get the name pair production. But in every interaction that we have seen the particles come out really kind of in these pairs here, such that charge will be then conserved. No net charge before, we have no net charge afterwards. The universe seems to be happy. Now, the photon at a very minimum has to have the energy that these two particles have in terms of their rest energy. That is, we created an electron and we created a positron. So if I were to take a look at the idea of mass, right, we have the electron plus the positron's mass that just sort of shows up in nature, right? Just shows up in the accelerator. The photon travels and all of a sudden it disappears from the universe. An electron and a positron show up. And the electron, you know, has this a half an MeV, and the positron has this a half of an MeV. And so if I add this up, you get something, you know, close to about 1, maybe 1.02 MeVs together. And so this is the minimum energy that the photon must have, right? The photon, for energy to be conserved, if we look at this idea of energy, right, the photon must have at least 1.02 MeVs of energy. That is something like a radio wave would not have enough energy to create an electron and a positron pair. The least amount of energy the photon can have is this 1.02 MeVs. And so if you were to look at this very carefully, 1.02 MeVs, and maybe we say, how about, I want to change the units here. I'm trying to think of probably the best way of doing this. And maybe we say that, 1 MeV is really this many EVs. So, we're gonna have to move the decimal here. We really have over 1 million EVs. And then probably, 1 EV is 1.6 times 10 to the minus 19 joules. And what I'm going to try to do, maybe I didn't have to actually do that. This will work. We can follow through here, but how about better yet? Let's do this. Let's forget this last part because we're working harder than we need to. What we really have here is something like this. And this is the minimum photon energy. And so remember, the energy of a photon is h times f, or I could call it hc all over the wavelength here. And I kind of like this right here because this photon has to have something like this many EVs at a minimum, and h times c is 1240 EVs times nanometers all over the wavelength. And so EVs are going to cancel here. And so if I get 1240 and I divide it by this 1,020,000 number, I'm getting some sort of wavelength here, something like 1.22 times 10 to the minus 3 nanometers. Now, the light that you see, right, goes from 400 to about 700 nanometers. And this is a thousandth of 1 nanometer. This is a gamma ray here. So you need a gamma photon to create something like an electron-positron pair. which are, some of the lighter objects to make. Now, if you wanted to create a proton-antiproton pair, then you need even more energy to do so. And, um, and so what you're really trying to do is, have, gamma rays at your disposal somehow if you're trying to make heavy particles. And this is part of the game that's played at Stanford, at Stony Brook, when Fermilab was up and running outside of Chicago and CERN in Europe, is that in the early 80s, Carlo Rubbia had this idea, whether it's all his or not, I don't know, but that is we can get matter and antimatter. Okay, so that might be for CERN, this is going to be a proton and an antiproton. And if you get them to collide, then they actually do the inverse of what we're talking about here. They disappear from the universe and a photon appears. Okay. Now, the photon at that point has energy, right? And it also will have, the momentum of the two particles, added together and so forth. But if you get these particles going very fast, that if their kinetic energy is high, and if it's high enough, you almost kind of don't even worry about the rest mass anymore. But if you have, maybe something like couple hundred times the rest mass in terms of kinetic energy when they hit, they create a photon that is so hot and so energetic that it has choices now. It can create an electron-positron pair with tremendous kinetic energies, and that happens quite often. It can create another proton-antiproton pair. That is, the proton-antiproton hit, they disappear, you have a photon, and a lot of times the most sensitive part of the of the actual detector is something about the size of like a coffee can or something like that. Sometimes that photon doesn't move very fast, and then it showers into particles. And what you're trying to do is create that photon to have enough energy to create particles that don't exist anywhere in the universe today. We don't see any interactions out there that have that kind of energy. Even the cores of stars are lightweights compared to the speed that we can get these particles moving in accelerators. But the idea is that we're seeing that the universe actually expand. And this is through observations with telescopes and so forth. So, 1,000 years ago, the universe was a little bit smaller, and 1,000 years before that was a little smaller. And, eventually, as you kind of start getting the universe, backwards in time, the particles and so forth were in close proximity to each other, which means that they were moving very fast. There's a lot of collisions. And the laws of physics under those circumstances are different than the laws of physics that we live with now. Right now, the universe is like 3 degrees above absolute zero. But the idea is that maybe it started at a very hot state, and everything comes from, it's possible, right? You just need a couple photons, and the photons can shower into all the particles and to make all the stars and everything that we happen to see. So you don't need a lot of space, right? The entire universe can just go down to the size of photons, which are just, and these are gamma particles, so there's not a lot of space there that's really needed. And, those photons can give rise to the mass that we happen to see in the universe. But in those circumstances, the photons have tremendous amounts of energy. And so that's what you're trying to do. When we look at all the interactions today, for the most part, you can describe all of nature with really 4 forces. And so you have seen the Coulomb force, that is the electric force between particles. And, that's a fundamental force. And then gravity seems to be a fundamental force. And then there are 2 forces that live inside of the nucleus that hold it together, because if you have a bunch of protons there, the Coulomb force should be, pushing them apart. So there's something else that's holding on to them. And that's going to be an aspect of the strong nuclear force. And then there's something called the weak nuclear force. When you change the environment of the universe, that is, when you make the universe hotter, then, and it's at this point, been demonstrated through countless collisions at the Stanford Linear Accelerator, that two of those forces meld into one single force. That is, the electric force and the weak nuclear force becomes what we call today the electroweak force. And so, for many years, for about 5 years, Stanford was creating photons by having an electron and an anti-electron pair hit, collide, create a photon. Then that photon has enough energy to create the particle that doesn't exist anywhere in the universe. The universe is too cold. And that was the Z and W boson, which are then the gauge bosons for this electroweak force. And so, you spend probably maybe 6 months or a year fine-tuning the accelerator, that is changing the speed of your electrons to find where you get the highest production of this particle that you want. Because, if you have enough energy, you can create anything lighter than that, as long as you can create a pair. So you can always create an electron-positron pair, which is not very interesting at this point. You can create a proton-antiproton pair, but if you're trying to create something that's heavier than that, that's fine. But you can create these lighter particles. They just carry off the extra energy in terms of their kinetic energy. So that can happen. So if you want to create some of these very exotic particles that maybe were just discovered in the last 15 years, like the Higgs boson, the theorists will work out their mass, and then you've got to get the accelerator up to the speed so that your proton-antiproton or your electron-anti-electron pair can be moving fast enough to create a photon that has enough energy to create that particle. And so that can happen. And like I said, this has been used to great effect by the nuclear physicists here in the last 30, 40 years. Just a very, very brilliant idea of getting something that nature does, and then kind of inverting the process to create these photons that we just don't see existing anywhere in the universe, but they can give rise to these particles, and then we can measure their properties and have a good idea of what kind of conditions and what properties and interactions they are capable of. And that's what research is really kind of all about here. So for example, if you wanted to create a proton anti-proton pair, then the proton has a rest mass of something close to like 939 MeVs. But for the charge to be conserved, since the photon carries no charge, you have to make the pair. And so, you have to create two of these guys. And so your photon at a minimum, 939 times 2, has to have about 1878 MeVs of energy. Okay. And so, if you wanted to do this, say at Stanford, where they use electrons hitting anti-electrons, you can see exactly how fast you need to make them go, because this is the minimum amount of energy that would be required. And so, if you wanted to, you could have an electron moving at some high velocity. You can have a positron moving at some high velocity. And when they hit right in this universe, what comes out of here is a photon. And the photon has to have, at a minimum, this much energy. And the photon just may move just a few inches before it becomes a proton antiproton pair, right? So that can happen. And so, this is the idea of pair production. The pair can produce a photon, or the photon can produce a pair. And so this is sort of the game that happens on the big scale today. of the big accelerators trying to double up their energy by having a kinetic energy, and kinetic energy turn into a photon of twice the energy that you have these particles going. When the Stanford Linear Accelerator started, it was just a straight tube, and you just put blocks of metal at the end of 2-mile long tunnel, and you just blast your electrons into that, and then look at the scattered debris, and then start working backwards about exactly what you're hitting. And this is how you start probing the world of very small here. And this is how the idea of quarks will be found experimentally at a place like the linear accelerator there. So for the most part, the arithmetic here with pair production is rather straightforward. What we don't normally see is maybe like photons coming from the sun just cascading into particles. Typically, to have momentum to be conserved, this happens kind of here on Earth because we have not a vacuum here. And so a lot of times being near a nucleus of an atom helps carry off momentum. And if you don't have something to help carry off some of the momentum at times, the pair production just never really takes place. And so here on Earth, that's typically not a problem for this to really kind of have a life of its own and be able to use this in the laboratory to very interesting effects. Okay, very cool. This is a very nice aspect of E equals mc squared. Energy, the photon can become mass, or the mass can become energy. Nature looks at them, essentially equivalently. So it really does work both ways. I think this kind of does it for our photon interactions. And what I want to do, though, is take a few minutes and, when people were looking at this, that light in the 1800s, which is demonstrated over and over and over again to be a wave. And then suddenly in the 1900s, it's behaving, at least in some experiments, much like a particle. And so, Louis de Broglie is going to show up and say, well, if what we thought was a wave is behaving like a particle, then maybe what we think are particles can behave like waves. And that's called the de Broglie hypothesis. And, that's going to be probably worthwhile for us to take a look at here. And so let's do that. So matter waves. So let's see here. What we should do here is just kind of recall here that a classical, momentum is an object's mass times velocity. And if you really want to get the answer right here, if the object's going fast, that mass needs to be the relativistic mass, which is the rest mass, all times the gamma factor, which is the 1 over square root of 1 minus v squared c squared. But what we have now is momentum of a photon. And so remember, this comes from really special relativity. And, this is the energy of the photon divided by c. And we've got several ways of looking at, the energy. You could write that as h times f all over c. Or, you could write this as, take out the frequency through distance equals rate times time. And we've got the frequency equals the velocity of the wave, which is really, for these waves, is always c divided by the wavelength. So I can take out the frequency here and put in c all over lambda. And there's already a c here. And so those cancel. And so the momentum of a photon is compactly written as Planck's constant divided by the wavelength of the wave that the photon is being carried in, okay? And so de Broglie is just kind of looking at this, and, I don't know too much of the history of, but I don't think he's being facetious. He's working on a PhD, and he's looking in the early 20s of what's really taking place here with a lot of these quantum effects, right? A lot of these photon effects now are popping up with the black body radiators, the Bohr model of the atom, the Compton effect, the photoelectric effect. Right? All these effects are being explained by photon physics as opposed to wave physics. And so, it's probably pretty natural to be asking the question, okay, if the photon can behave like a wave, or what I should say is electromagnetic, radiation, has this photon-like property, maybe it's that, regular particles that have rest mass, something other than a photon, may have some sort of wave-like properties. And so, take a look at what we got here for the photon. The wavelength has something to do with the momentum of the particle. And so I think de Broglie is going to basically kind of just look at this and say, well, okay, now for massive objects, and massive objects would be, matter. So for massive objects, maybe their momentum, equals something like h all over their wavelength. Okay. And you go, well, okay, this seems kind of odd, but this is kind of the hypothesis, right? That based on the velocity and the mass of the particle, their momentum, that there is this characteristic wave that is part of, or some sort of descriptor, or some sort of property of this object that happens to be moving, right? So now, we can get electrons moving, 99.99999% the speed of light at Stanford, but in our 20 years ago, when we had tubes in our TVs, we can get electrons moving pretty fast there. So let's just say, for example, we have an electron, and we don't need these big giant speeds that are only available at these big world-class labs. Say you have an electron and it's moving with kind of a modest speed here, so something like that. So 3 times 10 to the 7th would be 10% the speed of light. So this is, I think, about half that. So this is about 5% the speed of light. And I don't think this is a problem in TV tubes or anything like this to get them going this fast. So what de Broglie is saying is that there is a wave now that is part of this electron's, property, I guess it would be. And so, the wavelength here of this matter wave, its wavelength would be h all over m times v. And so for the most part, what kind of numbers do you get from this? Well, I'm just going to kind of put some numbers in and see what happens here. Here's 6.626 times 10 to the minus 34 joules times seconds for Planck's constant. The mass of an electron, that's something like 9.1 times 10 to the minus 31 kilograms. I don't need to worry about relativistic masses here. And I've got a velocity here that's, about, I think in my head, about 5% the speed of light. So I'm going to try this on the calculator and kind of see what, I'm going to get here. I get something like this. I might try this again just to make sure that I didn't hit something on the calculator incorrectly. But I get something about like this 4.9 times 10 to the minus 11 meters. Okay. So 6.626, 34 minus 1, 31 minus 5. 7th minus. Okay, so I'm getting about the same thing. Okay. Now, so this electron moving at this speed has this wavelength. Okay, this is the wavelength of the electron as it's moving. Now, if the electron is stationary, okay, so if the velocity starts getting close to zero, then the wave gets really big, and as the particle goes faster, its wavelength gets smaller and smaller and smaller here. Now, if you want to see this wavelength, what you need to do is an experiment, much like what you've already done, but with light. Okay, to see that light was a wave, one thing you could do is that you can put two slits in front of it, and you can do the double slit experiment. Okay. And this is where waves come in. They hit these two openings, and so most of the wave is basically absorbed by the screen, right? And there's just two little openings, and so each opening is a source of waves, and then you've got waves overlapping beyond the two slits, and this is where you get interference. And interference is a wave property here. So you can do something similar to that here. Now, the slits have got to be something getting close to the size of the wave itself. Now, for the light that you and I see, 700 nanometers, nano is times 10 to the minus 9. We're looking at hundreds of that. So really something like 10 to the minus 7. Notice this here. This is a pretty slow electron, and it's down to the 10 to the minus 11 power. So something like 1,000 to 10,000 times smaller than the light that you see. So now your slits have got to be really, really close. Okay. And what happened, in the 1920s is de Broglie, he writes these 2-3 pages up, I think, and that's his PhD thesis. And the professors where he is in France don't know exactly what to make of it, and they send it to Einstein and says, "Get a guy PhD, why not, right?" It doesn't take long for some experimenters to catch on here. And maybe making the slits that small is very difficult to do in your laboratory. But, nature's kind of already done that. And so Davison and Germer, a couple of American physicists, will get electrons and then essentially shoot them at a crystal, because it was already known that in a crystal that the atoms are in very specific sites, and then there's kind of nothing in between, right? So you have a bunch of space in between them. And so the Davison-Germer experiment, I believe, is going to win a Nobel Prize for that in the 1920s, and then de Broglie is going to win a Nobel Prize as well. And so if you have something like a crystal, right, you've got these atoms that are kind of spaced like so. And when these electrons come in and they have a certain wavelength, you need to get them going fast enough to even be able to fit between these atoms. But the atoms are you can kind of think about this as sort of like a slit here, and this is kind of like a slit there. But what ends up happening a lot of times in these experiments is that the electrons come in and they hit, and a lot of times they will reflect off. And what you will get here is many times something that what you would expect really of a wave. Typically, when I do this in the classroom, I get electrons. I can give them any voltage I want, and once you know the voltage, you can figure out their speed. And I have them hit some sort of crystal, and when they hit the crystal, you've got a beautiful picture in your textbook of if you have two slits, what you end up with is with a bright spot and then bright spots on both sides of it. You get this kind of symmetric, kind of one-dimensional little pattern here. But if you have a crystal, it's really happening in more than one dimension, and you kind of end up with this kind of a bullseye looking pattern. And so take a look in your textbook, you'll see this. And so what you've got is regions of constructive interference, and then you got regions of destructive interference where you're not seeing too much of anything happening. And it's letting you know that once, indeed that, these electrons are behaving, much like light would, where you get really, these diffraction and interference patterns and so forth. And, the double slit experiment, in the last 100 years has been done. And, it's really the heart of quantum mechanics. And so, if you do this with light and you have some sort of light source here. So here's a light bulb. You put a filter here, because what you really want is, maybe I put a red filter there. Sorry, red light. What you really want is monochromatic waves. And so, coming out of here then are these red photons. And you hit this screen that has these two openings, right? And then, downstream is your, the viewing screen that you're really looking at. And these waves come through, this opening, and they follow Huygens principle where they diffract. And so now you have all these different places here where you've got these, regions of overlap. And, that carries on to the screen here. And right in the middle, you get a big bright spot. And then you get a spot here, and you get a spot here, and you get a spot here, and you get a spot here. And this is sort of the double slit intensity pattern, right? And a lot of times it's looked at like a histogram where there's a lot of photons hitting here, right? So, something like this, and then none, and then some here, and then just a few here. So it's kind of almost like a bar graph or something. And so you get this intensity pattern here. There are places where the waves do not exist. They have canceled each other out, right? So there are these spots here of destructive interference, like here, right? And like here, right? These are spots of destructive interference. And so Davidson and Germer are showing that the electron is behaving much like a wave when it's interacting, with atoms in these lattice and so eventually, you're going to do the double slit experiment, but with not light, with electrons. Okay, so you just get a beam of electrons, make them all the same energy, put two little doors in front of them, and very interesting things happen. So now you try this with electrons. So you've got your beam of electrons coming, and you've got two very small slits. And sure enough, you get electrons hitting here and there and there and there and there, and here, and electrons hitting here and there. And so they hit in certain places and they don't hit in other places, okay? And so this is kind of interesting, right? You essentially get exactly the same thing on the screen that you get with light, except maybe it's spread out differently or something like that. And so you go, okay, what I'm going to do then is I'm going to shoot one electron at a time. Just shoot one and then turn the machine off, okay? And then maybe wait as long as I want. Come back the next day, shoot one electron, come back the next day. When you shoot one electron at a time, you don't know where it's going to land. But I'm going to put my pin here in black. But when you shoot one electron at a time, one will hit here, and then maybe the next one hits here, then the next one hits here, and then the next one hits here, and then the next one hits there, and the next one hits there. And as you shoot them one at a time, they land only in these spots where you would have constructive interference, okay? And so think about that. You shot one electron, and somehow on the viewing screen, you have an interference pattern. And so the way we understand how interference patterns are created is that the light if you're doing this with light, the waves go through both openings and then they diffract around the edges, and then you have regions of overlap, and that's where you have waves interfering with each other. Here, you shot one electron at a time, and yet it lands on the screen as though there is an interference pattern. There are spots of constructive interference and destructive interference. So that means the electron then went through both openings and essentially interferes with itself, okay? And how could it do that unless it actually is a wave, right? And so you go, oh, this is odd to even think that, right? This little thing like a meatball that's got negative charge, how can it go through both slits? And so, so being a clever experimenter, what you would do then is say, what I'm going to do is put a sensor at each opening and show you that this can't be the way it is, right? That is, I'm going to tell you which slit or which doorway the electron goes through. In the minute you do that, your interference pattern downstream on the viewing screen disappears, okay? And so this is really the heart of quantum physics, is that when the electron is left alone, okay, it is behaving like a wave. When it is touched by something, and whatever that is, it hits the screen, it hits as a dot. If it goes through one of the openings and you detect it, that means that it hits something of yours. For you to detect it, it becomes a dot, it becomes a particle. And so how you think about that, I don't know. But, it's almost like, you see these big, beautiful jellyfish, on these documentaries, right? They have this big aloofness to them. And the minute you touch them, right, they shrink up and, right, they square off and they become this small little compact thing. And the electrons are like that. When you leave them alone, they have this wave property. When you touch the wave, it becomes a particle. And so a very famous physicist that wins a Nobel Prize, one of the founding fathers here of a lot of this early quantum physics, basically says if you want to predict what electron's going to do, you treat it like a wave. You need wave mechanics to see what it's going to do, to have the right mathematics to predict what it's going to do, and that's the mathematics of quantum physics. However, once you detect it, then it becomes a particle. So anything in the future is a wave. Anything that you have detected is a particle, right? So you need wave mechanics to predict the future, but when you do actually make measurements on them, that's when they shrink up and become this particle nature here. And somebody tells you they understand this, right? I think they're lying to you, because we have no concept of anything in our life really behaving this way in front of us. So you just have no intuition on what these electrons are doing. And so this leaves you with this question, what is an electron? Electron is a particle that has negative charge. It has a rest mass of 9.1 times 10 to the minus 31 kilograms, which can be converted to about half an MeV, right? It has a certain charge distribution that can be probed and so forth. So it's a list of properties, but one of those properties is this wave property. And so if you get it moving fast enough, the wave becomes smaller and smaller and smaller, and that actually makes it maybe a little bit harder in some ways to detect and so forth. Now, something that may be lurking in your thinking, and if it is, I'd really be quite pleased, is that for Niels Bohr to get the answer right for what the electron was doing, right? He sort of looks at units. He's looking at other effects, right? He's using a lot of his intuition, and there's this mathematical requirement put on angular momentum of the electron in the atom, okay? And it gives us the right answers. And I think around 1910, 1912, when he's kind of doing some of this work here, I think maybe he doesn't, know exactly why that's the case. And that's why it's called a postulate, right? One of Bohr's postulates. Now with this wave mechanics here, if you apply the Broglie's idea, his hypothesis here, to the hydrogen atom, it's kind of interesting. So, let's actually do that. So, for example, let's apply matter waves to the hydrogen atom. Okay. And so, you recall that you've got this proton, but there's an electron in some sort of orbital, right? And so there's this first orbital, and maybe 2, 3, 4 times that distance, you hit the next orbital. And so, the electron could be here too, and so forth. And so, what comes out is that the electron orbital is quantized, right? And the way that Bohr starts working this out is that the angular momentum, the L vector momentum for a point particle is mass times velocity times r. And he says, well, this has to have something to do with a quantum number of Planck's constant all over 2 pi. And this gives you the right units. That is, these would be the units of really an angular momentum, on the right-hand side there, where n is just a counting number, right? The first orbital, the second orbital, the third orbital, and so forth. Okay. And so, this is what, kind of came about, in that earlier lecture. And this gives us the Balmer formula. And, it adds a little bit to the mystery, but it does explain a lot of things here. Okay. So now, let's take a look here at, de Broglie. So if we look at what Louis de Broglie is kind of telling us is that, the matter wave, and in this case, it's the electron, its wavelength has something to do with h all over the object's momentum, right? And so, let's really sort of kind of apply this. Now, the Bohr circumference in the hydrogen atom, those radii or something like a naught times n squared, right? So like a naught n squared, but if you want a circumference, the circumference is going to be 2 pi times that radius. So that's the circumference that, we're picturing the electron really kind of move around in, something like that. Okay. Now, if this electron is left alone and nobody's touching it, right? It's when it has an interaction with something, is when it seems to become a particle. Left alone, it's a wave. Okay, so if you imagine a wave, but being around somehow the nucleus, you had to have a whole number of waves. That would be an assumption, but we have never seen something like half an electron. Right? So if an electron is this matter wave, then the wave has got to fit on the circumference. And so, maybe, one way you might be trying to, imagine this, if you've got the proton here and, you have this orbital, say this first orbital out here, for the wave to fit, right? So a wave is something, that looks like that. There's one wave. That has to fit on this circumference. So when you start it here, right? So maybe that's halfway, maybe it has to do something like this, hit here, and then it, comes underneath and it does, something like that, where this part is that part, and here's the part that's underneath. And so maybe, it has to look like that. Or, maybe you can get, 1 whole wave, 2 whole waves, 3 whole waves, 4 whole waves, 5 whole waves, maybe like 6 whole waves or something like that. But you have to have a whole number of waves sitting there. Otherwise, the electron sort of like doesn't exist, right? The matter wave doesn't really kind of, fit there. And so, if we apply this, then this idea of the circumference here it's got to be like a whole number of waves, like one whole wave or two whole waves or three whole waves or something like that. And how big is the wave here? Well, the wave is something like we have above from the de Broglie hypothesis, that it has to look something like that. And so, what are we really left with here? We're left with n times h all over 2 pi equals m times v times r. That is angular momentum, and here is the Bohr hypothesis, right? And so that the electron forms some sort of wave, and you have to have a whole number of waves, and in that state, and with one proton, with one electron, there's a certain energy level, so the electron has a certain speed, so it has a certain size wave. That wave has to fit someplace, right? And so if you just go a little bit bigger, then suddenly that wave doesn't fit. It doesn't quite close up anymore. And so then you don't have a orbital, right? The wave can't sort of sit there. But there are certain spots where the wave can exist naturally. And so suddenly now, we're getting something like waves being applied to something like an electron being left alone in nature. And we have now an explanation to, one of the Bohr postulates. Why does the angular momentum have this the certain mathematical requirement? Well, it looks like because the electron has wave properties, and you need constructive interference. You need to have a whole number of waves to be able to sit on an orbital for you to have an electron there. And so if you have a whole number of waves, then the mathematical requirement that we've got sitting right here is identical to pretty much what Bohr just postulated about 15 years earlier or something like that. So very, very interesting, how nature starts working out on this level. Now, this matter wave, I would think that physicists, just about universally would agree that any object with mass, okay, that is moving has a matter wave connected to it. Okay. Now, let's say that we get something like, for example, here. Let's say that we've got, a 1,000 kilogram car moving at 30 meters per second. Okay. Is there a matter wave connected with a car in motion? Well, what's a matter wave really look like? Well, this is really something like what we've got right here above, right? H all over m times v. And so H is Planck's constant, 6.626 times 10 to the minus 34. We got joules times seconds. And the mass here is 1,000 kilograms. And we've got a velocity of 30 meters per second. Okay, so if we really look at joules as work, right? Newtons times meters, and the Newtons got, mass times acceleration and so forth. And we follow all the units through here, we're going to end up with just meters here, 6.626 E34 minus, divided by 1,000, divided by 30. And let me try that one more time. 34 minus divided by 1,000 divided by 30. And I think I'm getting something like this, about 2.2 times 10 to the minus 38 meters. Okay. So if that car has a matter wave connected to it, and I think most physicists would say, yeah, there's a matter wave connected to it. Look at the size of the wave, and then come up with an experiment for you to be able to detect a wave of that size, right? And so, wave properties might be something like interference. Can you have this car go through two slits and show this wave characteristic? And then suddenly, you get to a point where you almost practically can't do the experiment, right? So now it's going to be difficult to detect a wave of that size. It's just so small. And so probably indeed a car going down the road has the Broglie wavelength or a matter wave connected with it. But the wave is so small, it's something that's not part of our intuition because we're not seeing it, right? We're not detecting it. We can't even detect it if we're looking for it, not a wave the size here. So it's just not part of our everyday, experience and intuition and so forth. And so, this is a very interesting aspect of quantum physics. And something that Einstein did not like really at all. That when a particle encounters something and you want to make a prediction of what's going to happen, you treat it like a wave, and waves have got size, right? And so what you end up getting are laws that are probabilistic laws. Now, when you drop a baseball, it does the same thing essentially every time under the same conditions. Now, when you do this with an electron, some sort of experiment, it doesn't do the same thing every time. Right? Nature is not deterministic on the small scale like it is on the big scale. On the big scale, the baseball will always do the same thing. The electrons don't. All you can do is say, well, the wave, there's a probability that part of the wave goes here, part of it goes there, or something like that. And so you end up with laws that are probabilistic, something that just really drove Einstein nuts. Right? So he'll spend considerable time trying to undo the laws that are being developed, but they just keep working. And he even wrote papers that said, well, if this is really true, and nature really works this way, and then he come up with some kind of absurd conclusions. All those conclusions have been essentially found experimentally, like the Einstein-Bose condensate, where you can make material and get light waves to go through just at a meter or two per second instead of 3 times 10 meters per second, so forth. Something almost like molasses to these electromagnetic waves. And so it just keeps on working and working and working and working. And quantum physics, built this calculator, built your phone. It's all working off of, the processes that are essentially quantum physics at this point. And so quantum physics is just being tested every time you turn something like this on. And so it's just a testament to the human imagination of what's taking place here. And being able to use these properties to build technologies. And so, we've got, considerable technologies built on, the properties here of quantum physics. So it's hard for us to wrap our head around what's going on because we want to be able to picture everything, but we don't live on that scale. So, there's no reason why at that scale, you should be able to picture, exactly what these things are doing. So it's something a little bit mysterious to our everyday experience, but the math and more importantly, the experiments tell us over and over and over again, probably a billion times a day now, right? That the properties that we have uncovered are indeed governing small particles and their interactions with other particles and so forth. So it's a very interesting branch of physics that didn't really exist, until really about 1905 or something like that. And this would be something that all physics majors would take, right? You're all going to take courses in nuclear physics and quantum physics and modern physics, and all graduate physics students are going to be taking more advanced courses and that sort of thing too. But the ideas here are exactly the same. So very, very interesting. And this will probably conclude our physics here that we'll call properties of photon interactions, and here with matter waves. So this gives you something to think about. It keeps you up at night. You will not be the only one. But this is the way nature seems to be working here. So if you don't like it, that's okay. You're in good company, because Einstein didn't like it either. It's just it just turns out that experiment just over and over and over again keeps telling us this is the way nature works. So give this a good thought, and I will see you soon, and you can tell me what you think here.